Hi, I'm Alexa, and today we're going to be talking about the ThunderScope front end again, this time from the perspective of the low frequency path and the AC-DC coupling. So for this video, we can basically just zoom in on this buffer here and take a look at how it works. So the first thing to keep in mind is that this buffer is composed of these two parts as a kind of cohesive whole. They're working in a composite loop mode, which means that the output of this op amp goes into the buffer through this in-aux pin, instead of basically recombining at the output of the whole thing, which is actually a thing that I did for the Rev 1 circuit, where this buffer was just another JFET and some accoutrements. So the reason you want to do something like this, have a separate buffer for high frequencies and a op amp for low frequencies, is the buffer is not very good at DC accuracy or low frequency noise. It has a lot of noise there. And the op amp is just very good at all that stuff, but doesn't really have the bandwidth we need way up high. Like, this thing has a gain bandwidth product of 11 megahertz, and this thing will happily do a roughly 1x buffer to 3 gigahertz. So we want to kind of combine their strengths. So let's look at the op amp first. And this is actually where AC and DC coupling come in, because this op amp has one of two kind of profiles here for frequency response. It's going to look either like this in DC mode, which is when the switch is turned on and you have a DC path through it. And then that 3 dB point is going to be determined by the gain bandwidth product that I just mentioned of 11 megahertz. And that's actually for the OPA 140, which is what we're using now, not the OP07, just as a note for completeness. And then you multiply by the aux gain of this path here, which is 0.2, and then the ratio of this divider here, which we'll call 10. So that ends up being 220 kilohertz. And then way down here, you can also choose to disable the switch, leaving the capacitor in the path, and then you basically get a high-pass filter consisting of these components right here. And then that is going to look like that instead, right? So this is DC, this is AC coupling. And that 3 dB point, as I mentioned, are these two components acting as a high-pass filter, which basically is 8 hertz, very low. And then we look at the buffer here, which also has a similar thing going on at the low frequencies. Here, I'll just delete the whole thing so that we can start over with the buffer. So this buffer has that same thing going on, high pass filter, at combination of these two components. So actually that is the same as the high pass filter for AC coupling. Now, it doesn't have to be. I basically just chose it so I could reuse these components. But given our result from the previous video, I'm probably going to shift that around a little bit. But that's basically what it looks like. The same 8 hertz down here. And then it basically continues on for a long, long time because this buffer has plenty of bandwidth. And then we can attempt to draw the other path here. So it would look like that, or like that. So this crossover region is important. To make the response as flat as possible, we essentially want these two poles to be very far from each other. So that's why this is like 8 hertz and this is 220 kilohertz, which is the difficulty I mentioned about increasing this capacitor. Because essentially you start moving that pole closer and closer, and then you start getting some kind of wiggliness in the crossover, which is not great. Hey, I'm the editor. I've come from the future to tell you that C30 actually significantly impacts the shape of the crossover response. The other criteria for the kind of flatness of the gain response is for this ratio here and this ratio here divided by each other to equal the gain of the buffer, right? And that gain is not exactly 1.00, as we know from before. It's actually 1 plus, actually just minus 2% to 1 minus 5%. So that's another thing to be weary of, and that's why there's actually a trim pot over here to adjust that gain. Let's see what it looks like when the gain is not adjusted. Now that's not a very square wave. Now I know what you're probably thinking. The probe's not compensated, right? Well, this is actually a 1x connection directly to the function generator, so this is not the probe. This is clearly some sort of difference in the low frequency gain and the high frequency gain. How do we know that? Well, let's look at this square wave in detail. Let's actually turn off the other channels and get... Yeah, there you go. So weird watching this on a 1080p screen. So this edge here has the high frequency content, and then this flat top here is all like the lowest frequency content basically. So note that this ringing is not like really, really high frequency. It kind of gently tapers off. So to me, this seems to indicate that there is an issue with our crossover. So maybe the really low frequency gain is actually lower than the slightly higher frequency gain after the crossover point. So there's one way to really find out here, and that's to do an impromptu bode plot. What the bode plot is telling us is the low frequency gain, way down here, is way, way lower than the high frequency gain. Thankfully, as we discussed earlier, we have a solution for this exact problem, and that's this potentiometer right here. We're just going to need to tweak it a little bit and see if we can bring the gain up to the level of the high frequency gain. So now that we know exactly what's going on here, we also know how to fix it. So I'm going to go into the ThunderScope here and tweak that potentiometer, and you should see this square wave begin to change. That seems like the wrong direction. There we go. We seem to have leveled out the top, and we get a little bit of peaking still. That is going to be due to the crossover region, which is governed by the capacitor in the op-amp feedback loop. So if we change that capacitor value, we can probably further optimize that little bit of peaking out. And that's actually for the OPA 140, which is what we're using now, not the OPO7, that C30 actually significantly impacts the shape of the crossover response.
How'd you get into this spot? You played yourself.
Oh, I'm going to have to recalculate that. So lesson learned. Don't make last-minute bomb changes. I got so worried about the low-frequency noise and the DC offset that the OP07 could be contributing that I switched over to the OPA 140, which is better in those respects, but I forgot to change C30, because C30 does depend on the op-amp you use. So I looked at the reference design from the Buff 802 datasheet, which includes the OPA 140, and I used the value they recommended. That was too low. It actually made it worse, so I had to go higher. I ended up settling on 220 picofarads. Oh, and also, I changed this value here to 1.2 nanofarads when I was testing out the 56 picofarad value down here, and it didn't really change much, which is good for our input protection specs, as we mentioned in the previous video. Now let's see how that square wave looks with these new values. I never thought I would be this jazzed to see 90-degree angles, but I am. It looks like 220 picofarads did the trick. This is a 10 kilohertz square wave, same as what you were seeing earlier. And just to kind of sweep it around a little bit in frequency, we're going to go down to 1 kilohertz. And that doesn't really change anything. Still a very nice looking response. And then let's go up to 100 kilohertz on near the top end of the low frequency path gain. And still looks good. And I guess I should also show off AC coupling, given that that is still part of the topic of this video. So let's shift that up a little bit. And then we want to shift it back down. So here we go. DC, AC. So yeah, I'm glad I could share the debugging process, because even when you've worked on something for a really long time, you still make mistakes every once in a while. But the most important thing to do is understand the system and understand what you need to change to fix that mistake. So I hope you found that interesting, and stay tuned for the next video on DC offsets.